Alright, welcome back everyone. This is the spring semester for Natural Science talk. We have quite a lineup, and I think it works actually very well to bundle always two speakers up. So we have today brain researcher and informatics researcher. And I hope we have in the audience not only brain researchers and not only complex system researchers. So this is really a talk series that helps you kind of transfer methods, algorithms into data sets between the disciplinary boundaries, as long as you can have your own processing network into the nodes and edges of somebody who's presented. I hope that was good. Because today are done by the two postdocs we have in Indiana University Natural Sciences. And the first one is Joaquín. And his bio was posted, just for your information, he's an associate research scientist at IUNI, and he's also an assistant research professor in the Indiana University School of Medicine, Department of Imaging and Radiological Science, up at IUPUI. And he really is running not only this course, but also two campuses. And the second speaker today is Neil. He is part of the Complex Systems Institute at the School of Informatics and Computing, and also postdoc in uni. And he also teaches, in case you would be interested to learn more about what he's presented today also as a background for it. He's teaching mining social web. And his PhD is in mathematics and computer science. He has opened up all kinds of different positions, and he was very early with Alzheimer community. So welcome everyone, and just speak for 25 minutes presentation, 5 minutes discussion, and 5 hours.
Okay, thank you very much. It's a pleasure to be here. It's always a pleasure to talk about the research we're doing through uni and also in collaboration with the School of Medicine in Indianapolis. I'm going to be a little bit fast today because I know the timing is very precise, and I wanted to talk about several things so that we enhance the possibility of collaborations and discussion. The title is, I probably will say this disease only once, Mapping White Matter Neurodegeneration in the Human Connectome, a neuroscience study of hereditary diffuse leukoencephalopathy with spheroids, from now on HDLS. I'm going to touch also the aspects of the research related with brain connectomics. Let's start about the human connectome. The approach of the human connectome to understand the brain involves nodes that represent gray matter regions and edges that represent the most prominent white matter fibers that are connecting those regions. We have a lot of interest in understanding the integration of information in the brain, and how can we characterize that by the length or the efficiency of the shortest paths. We also have another interest that I will explore briefly later today, which is on how hidden are those shortest paths, and how can this bring ties between the structural connectivity and the functional connectivity. Nowadays is a really exciting time to go into brain connectomics because of the things we can collect through the scanner. We can collect, we can make estimations of tissue, white matter, green matter, CSF. We can actually parcellate the green matter into meaningful ROIs. We can do that through functional connectivity basis or also through the structure of gyri and sulci. Not only that, but nowadays we can develop models that allow us to track the most prominent fibers to the white matter that are connecting different green matter regions. And not only that, we can complement that with something that is very challenging, which is actually to connect the structural connectivity, how the fibers connect to different green matter regions, with the functional connectivity while the subject is developing a task or is doing the so-called resting state. So in our collaboration with Olaf and with others, we have a strong interest in trying to understand the relationship between these two matrices. Think of it as matrices that are relating all the possible green matter ROIs versus all the possible green matter ROIs. Every time you see a blue dot, we found actually physical fibers that are connected to those two regions. And on the figure on the right, what we're aiming to represent is the level of coupling in the activity of those two regions across time. In this particular case, it's on resting state, but we can actually do that through any other task, a decision-making task, a visual task, etc. So we can think of our favorite two ROIs, and we can check whether they are directly connected through white matter fibers. We can actually have an estimate of how many fibers, and I will go into that later. And then we can ask whether they are actually coupled, functionally speaking, during the task that the subject is performing. This has endless possibilities in many ways. One is what is the green matter parcellation that we're going to use? What is the level of resolution in our structural and functional connectivity matrices? So you can think of different subsequent divisions of the green matter so that we have more rich, more detailed connectivity matrices, maybe with more noise and also with more individual variability. Or you can go to the left part of the figure, and then you can divide the green matter into a reduced number of ROIs, but still can be meaningful depending on the research that we're being focused. From the neuroscience perspective, we aim to go to the right as much as we can, because then the number of nodes, the statistical significance of the findings, and the level of resolution allow us to make more precise statements about the structural and functional connectivity. This is a particular case that we found when I joined, when I started my agent appointment in Indianapolis. We were aiming to go towards individual connectomes. What do I mean with that? One thing is to collect 100 subjects, do all the processing, do an average, and try to find general, strong findings on population average connectivity matrices or structural connectivity or even functional connectivity. The challenge when you move to clinical is that you want individual connectomes. You want to see what makes difference one particular subject with respect to other, aiming that will allow you to make statements among different diseases. Think of it, Alzheimer's disease, its more mild version, mild cognitive impairment, frontotemporal dementia, schizophrenia, et cetera, et cetera. So nothing was working really well in the processing pipelines that I was given, in the sense that we couldn't find differences between groups practically no matter what we did, and we did a lot of things. So I asked, give me the most severe case of any neurodegenerative disease where you tell me, Joaquin, you better find something, because otherwise this is not looking good. So we got that case. It was this HDLS case. It's two siblings. We actually have two visits that is very valuable. This is a very rare disease. It's very difficult to find patients. We had two visits, and there are two siblings. One has the disease and one hasn't. So we have and they are very similar in age. So it's a very good match to make statements about individual connectomes and whether we're able to do reproducible results across the two visits. If any, the only thing is that the two visits were 18 months apart. So you can also expect some changes no matter what. But this was very, very harmful. So then we ran the processing pipelines of the structural connectivity. And basically, what we found is that there was nothing. We couldn't find differences. Even though when you check on the T1, on the tissue, even not being a clinician, you actually see that the patient is very affected and it has big portions of white matter that was compromised. We couldn't really find anything. So I summarized my position in this figure, which is I started a long journey, which, to be fair, Joy should be in this picture also, where we were aiming to find reliable individual connectomes. We can do on the network science very advanced, sophisticated, even fancy features, and I think we're really good at that. But if we don't have accurate, reliable individual connectomes, we cannot really make strong statements at the individual level. And this is crucial for us because many times this data is given to us, and we really need to become really good at that. So in the literature, there are papers. I remember this paper that Rick found a while ago, where it's basically we should just drop this and abandon this. It's not doable. There are other people that are more positive, and we're very lucky, I don't know if he's in this room, of having Franco Pestilli, which is actually aiming to bring solutions to these problems so that we can get more and more reliable individual connectomes. It's funny that my figure is on a path, and we found this software called Camino that was part of the solution. Camino means path in Spanish. That is, I think it's a very, very good tractography toolbox. It allows you to run deterministic and probabilistic tractography. We combine that with FSL for registrations and distortion control and this kind of phenomena in the data. And everything is controlled through MATLAB. So we have a pipeline that takes the raw data. There is a part that involves a visual QC that we do manually. But rather than that, everything goes, and it goes all the way until we have the structural, in this case, the structural connectivity matrices. I'll leave this for another day, but we also have a pipeline for functional connectivity matrices. The way it works is that we try to put all the sources of information that we have. We don't just put seeds everywhere cross our fingers and see where the fibers end up being. We actually account for segmentation of the tissue, green matter, white matter. If it's present in the patient, we also include something that is called FLAIR, which is a special sequence that accounts for damage in the tissue, regardless whether it's green or white matter. This is very important because I can tell you, in subjects with a lot of lesions or very dramatic neurodegenerative stages, the automatic tissue segmentation becomes a real problem. Basically, FSL, SPM, your favorite freeze hardware software, they really don't know what to do with that tissue because it just doesn't add up. So visual QC and adding sources of information that take care of that is very, very important. We also did something that we didn't invent it, but I think we're becoming very comfortable using it. You have always to choose between deterministic and probabilistic tractography. Basically, think of it, deterministic is, I'm quite confident there is a fiber connecting these two ROIs. Probabilistic is, I'm as confident as with certain probability that these two ROIs are connected. The problem with deterministic is that you can claim it's very limiting, because basically what you're doing is to assign a unique directionality on every voxel of white matter. There is an intermediate solution where you don't go to probabilistic, where you can be in the problem of placing too many seeds, exploring too much the probabilistic space, and finding that pretty much everything has certain probability of being connected to other things, to other ROIs. The nice thing of multi-tensor modeling is that it's deterministic, but it allows to find patterns where maybe in one voxel there are fibers going in one direction, and there are other fibers going in another direction. So it nicely solves problems of fiber crossing. It has some limitations in a way that you don't deal with the problems of probabilistic tractography. Anyway, for those who are interested, we are also including probabilistic tractography in the pipelines so that one could run whatever he thinks is better. We always need a green matter parcellation, and we end up with these nice pictures that are resembling the most prominent fibers that are connected different pieces of green matter in the brain. At the end, it's all about matrices for Olaf and I, and we always end up with matrices where in the upper triangular, you see whether they are not directly connected, the ROIs, and in the lower triangular, in this case, I'm reporting the average FA value, which is an estimator of the level of integrity of the fibers. In the case of HDLS, we were very excited with this pipeline because even if I don't tell you who are the visits of who, it's kind of easy to see that there are two matrices here with more points. That means more fibers, and that they look alike. I'm talking about the first row. There are two matrices that look alike, and that they have way less fibers. I'm talking about the matrices in the second row. Well, the first row is the first two visits of the healthy control. The second row is the two visits of the patient. So something that we knew, we could see it in the T1, we could see it in the FLAIR, but we couldn't see it before in the structural connectivity matrices is now reflected, which is the subject at the bottom has a lot of lesions in white matter that, as a consequence of that, is producing a lack of connectivity. Actually, I can tell you, if you look at the second quadrant, top right of any of the matrices, those are the interhemispheric fibers, are fibers that are connecting regions from different hemispheres. You can see how it's especially aggressive that the patient is missing of many interhemispheric fibers, which makes sense because we actually check, and it has a big lesion in a white matter region that is called corpus callosum, where most of the interhemispheric fibers go, with the only exception that they always go also in the anterior and posterior commissure. So this was very good news. And actually, we got very excited because when we confront in a scatter plot, in this case, it's average FA. If we confront number of fibers, the plot is very similar. When we confront the first visit with the second in the healthy control, and when we do the same in the patient, we actually have a good, of course, to some extent, but a good reproducibility. The connectivities that we find in the first visit in the subject, when he came a year and a half later, we could also see most of them, and with the same level of either integrity or level of connectivity. And this is very important for us because otherwise, unless you have longitudinal, you cannot really trust if what you're measuring is the individual variability of the subject, or it's just noise. That is, it doesn't make a difference if it's the same subject the second visit, or it's just yet another subject in the first visit. So we're giving a lot of importance to these kinds of properties. Then we did something very similar, very simple from the network science point of view. We just went to the concept of shortest paths. The only thing that we're trying is to find what is the visitation of green matter nodes through the connectivity that goes through white matter. that makes the shortest path between every two ROIs. You can measure that in two ways. You can count the number of edges or fibers that you're going through, or you can actually work on a weighted distance, where if there are more fibers, the distance is smaller, and if there are less fibers, the distance is longer. So we check that on these two subjects. Again, first row is the healthy control across the two visits. Second row is the patient. And the scale is the same, the color scale is the same for everybody. So you can see as it pops up that the interhemispheric connections are more red in the patient, meaning that the shortest path in terms of number of edges is actually longer. If we do the same exercise with the distance, it's actually the same. And this was very, very good news for us, because then we can measure very, very elaborated measures on network science. But we really wanted to see something that it was very clear, which is that this subject is missing connections. It's missing many connections interhemispherically, and that has to have a consequence in the networks that we measure. Because even though we love networks and network science, what happens in neurodegeneration is cellular death, tissue damage, that affects our voxels in MRI, and then when we model the connectivity, that affects our matrices. And so we have to see that when we see something at the tissue level, it has to have consequences at the network level. In particular, we found a number of regions that were more affected than others. And we also care, although I'm going to go very briefly on this, about the segregation, how the structural connectivity that we find across the subjects is leading to different communities. So if we check and we try to find a solution of communities that matches the two visits of each subject, you can clearly see how there is no single module in the patient that accounts for regions that are in different hemispheres, which again goes in the line of missing interhemispheric connections. So the module 2, there is a kind of cyan blue in the healthy control. It falls apart in the patient. Very briefly, we're willing to expand these approaches. And this goes back to many discussions that we have with Olaf and all collaborators about shortest paths. So basically what we're willing, and I'm going to be a little bit fast, is to say that, well, shortest paths is a very good approach. Probably when you have patients and controls and the patients have very prominent damage, it's probably a good way to explore things and to see how connectivity is altered. But I think we can do better, because basically nowadays the clinicians in neurodegenerative are moving along to going to the earliest possible diagnostic so that we're able to find something, so that first, it allows for a diagnostic, and second, hopefully, it allows for a prognostic. How fast is going to the disease to develop? Or can we do something? Or can we establish types? Or these kind of things. So as almost always, people from physics already thought about this, although not in the brain. So shortest paths are very important, but they are very important only if you're aware of the full map of the connectivity. How do I know how to go to my car? Well, if I know how to go to my car, it's because I am aware of the map of the campus. Otherwise, it doesn't matter how close in my car, I just won't be able to make it. So routing requires knowledge. And some other people from physics also pointed out, well, that's true, but maybe there are some topologies in networks that even if you don't have such knowledge, favor the communication without it. So this is what I did for a year, going from Bloomington to the Neuroscience Center. And I checked on Google Maps. And basically, it's 58 miles, and I have to make 13 decisions, okay? Make a left, make a right, join the highway, do this, do that. And I'm famous for being very bad at this, so it's kind of funny that I do this research. So then if I ask for a second shortest path, that's 81 miles, it's through Columbus. You don't want to do it, it's too long, but it involves 10 decisions. Why is this point? Okay, let's make the most simple model ever. Let's assume that every decision has 0.5 probability, because assuming I just don't know what I have to do. So basically, and I'm going a little bit quickly, the amount of information that I need to follow the shortest path, which is 58 miles, which is through Martinsville, I need 9 bits of information. However, going through Columbus, even though it's longer, the shortest path is longer, the amount of information that I need, because I need to make less decisions, is smaller. So I just need not even 7 bits of information. So this goes to the idea that we can learn that one path can be shorter than another, but also can be more hidden than another, under the assumption that you don't have full knowledge of the network. Well, long story short, we found last year that this is actually a great predictor of functional connectivity. What we're seeing on the top left is, on the lower, is the actual empirical functional connectivity matrix. I don't need the upper triangular because it's totally symmetric. The functional connectivity between A and B is the same as the functional connectivity between B and A. What you see at the upper triangular is the search information across the two. And if I make a scatter plot, we see a strong negative correlation. We're modeling 500,000 interactions between regions in 1,000 gray matter parcellation. And we have a practically minus 0.6 correlation between how hidden are the shortest paths and what is the level of functional connectivity. I'm going to advance a little bit. We give a lot of importance to checking that our results are not just by chance, or maybe because of the level of density of the network, or maybe because of the degree distribution, just because there are some hubs, maybe that explains everything. So we disorganize the network iteratively, and we always check that our predictors of functional connectivity based on structural connectivity actually drop, which is a very good sign. It means that we're capturing something that is beyond the number of edges and beyond whether there are certain hubs that are taking all the centrality of the network. Okay, so in summary, this approach, it gives us good hope that the concept of knowledge of inside the network, it is actually related to functional connectivity. And we're willing to expand on that. I call this slide the shortest path paradox. Maybe you've seen Lucy, the movie. Again, this idea of we use 10% of the brain, or 15, or 5. Well, if we focus only on the shortest paths, and I ask how many edges are part of at least 100 shortest paths, which is basically asking for nothing, that's the second matrix here. Basically, I want you to have the sense that it's less populated. If I ask how many edges participate in at least 100 shortest paths, which is nothing, we're talking about 500,000 interactions, 2,000 edges is actually half because it's symmetric, only 1,000 edges. So we're doing that. We're putting all our effort in getting robust, reliable individual connectomes. And at the end, if we only focus on shortest paths, we're putting all our effort in a very small percentage of connections. So the question is, shortest path should be the only one? Okay, so I'm going to use a proverb here, and I'm close to be finished. We can do better than that. We can expand the concept of shortest paths, asking for the second shortest path and the third shortest path, and whether that reduces the amount of information that we need. This is actually, I'm quoting myself many times when I'm trying to get to a new place. I'll promise you I'll reach the destination, but I cannot really tell you which path I will take. Hopefully a good one among a set of possible ones. So the idea is, let's say I'm going to, from the source to the target, A to D. I can tell you the shortest path is A, B, C, D, because of the weights I impose on the network. And that requires 1.7 bits of information. If I take the second shortest path, that's 2.66. The magic happens now. If the only thing I promise you is that I will take either the first or the second path, I just need 1.5 bits, which is less than having promised any of the first two shortest paths. Let's make it more complicated. Let's add another node. First path, second path, third shortest path. Now I'm going to make my promise of either the first or the second. That's already cheaper in terms of information than any of the three. And if I just relax my promise to I will take any of the first three, this drops. This measurement doesn't drop monotonically. It depends on whether there are overlappings between the shortest paths, because then you're reducing the amount of information that you need by having more choices that anyway will take you to your promise of taking one of the first case shortest paths. So we're working in that direction with Andrea, that is present here, trying to see if that helps to even predict better functional connectivity. Let's not focus on how hidden is just the shortest path, but the first case shortest paths. Okay, so I hope I have convinced you that information theoretical elements of network science actually are able to predict probably better than other features the functional connectivity, which should give us a lot of thinking about how is the dynamics and the relationship between structural and functional connectivity. I'm going to skip this, and I'm just going to make a point. There are measurements on integrity of fibers that are getting a lot of attention in the literature. One is fractional anisotropy. Fractional anisotropy is aiming to tell you the level of integrity of a fiber, but it's the average of the fiber. And I'm finishing with this example. Think that we're going from A to D, except I'm not showing you what is after the curve. Well, as soon as I have one of this, or maybe one of this, even if on average this road is fantastic, this is not a valid route for communication, right? So this is a problem with averaging across fibers. And let me make this example. This fiber is perfectly healthy except in a few voxels. This fiber is not operative. So we're developing with Joy ways of developing measurements of integrity of fibers that are more sensitive to damage, so that even when the fiber starts to be in damage, and I'm thinking of mild diagnostics in clinical applications, we are able to find something in the network, in the structural connectivity. Okay, I hope I did it on time. Sorry if I went too fast. Thank you very much for your attention.
Thanks. Very interesting thought. I was wondering, and maybe this is related exactly to this bias that you shared about the lesions, whether fiber is also, whether like the capacity of fiber is also important. Like in computer networks, for example, when you want to route targets, you want to associate lesions so that you have computer capability. So the best path is not anymore the shortest path, that's the widest path.
Absolutely. So two things. Yes, I totally agree with you. There are two things that we can do. So first of all, GIG has a lot of assumptions per se, because I'm talking about the structural connectivity as a communication network, but also from the neural point of view, there happens a lot of processing. So that doesn't ensure that necessarily the shortest path is the one where the information should be processed all the time. So that's a limitation first. And second, we develop estimators on the strength of the connectivity based on what we call number of fibers, which is if there are more connections between two ROIs, we claim that that's a shorter path than if there are less connections. And actually, we have repeatedly evidence in many data sets that that correlates with the functional connectivity. So if we only look at the pairs of ROIs that are directly connected, whether if they have more fibers, the functional connectivity in resting state tends to be higher at the level of a correlation of 0.5, 0.6, depending on the models we use, which give us an evidence that that matters, the amount of connectivity or the level of integrity of the connectivity. Yes?
Is there any way to determine what kind of fibers will be damaged across the
There is more research on this on the gray matter. There are models where they claim, well, Alzheimer starts hippocampus, entorhinal cortex, and then spreads through the cortex. I haven't seen this on white matter, but I think the question makes a lot of sense. Like as a cascade effect, this fails, and then because this fails, this other thing, yes, absolutely. I haven't seen that much in the literature on white matter. So far, it's more common in the gray matter, until the point some people build the structural connectivity matrices with correlations between gray matter cortical thickness of different ROIs, which I have some trouble calling that structural connectivity, but it's an approach that sometimes is done. Thank you. Thank you, Emilio, for this. Thank you very much. Okay, so I just take this. This was super useful. Thank you so much. Yes, thank you.
Can you hear me? Cool. Okay. Well, first of all, I want to thank Katie for the invitation. It's great to see all these familiar people and faces around. And after the great talk by Joaquín about real science, today I'm going to talk about Twitter. Sorry about it. So, well, my talk is called The Rise of the Social Bots. And in particular, I'm going to talk about how to fight deception and misinformation in online social media. I want to start with a sort of a consideration that I suppose everyone will share with me. Let's all agree that during the last century and a half, we moved from essentially a paradigm in which information diffusion was broadcasted by probably some very limited amount of individuals, and the credibility of these individuals was sort of broadly acknowledged, in this case, for example, President Lincoln, later on by more traditional media like newspapers, and later on the TV and so forth and so on. Nowadays, we are living in an information revolution, another phase of this information revolution in which everyone becomes not only an information consumer, but also an information producer. So in this either democratic scenario in which everyone can go online and tells their own opinions or spread some facts or share some information, there are vast societal consequences. Think about, for example, the Arab Springs or all the social protests and social movements that we witnessed during the last 5 or 6 years, including, Occupy Wall Street in the United States, the protests in Spain, the Cinco de Mayo, and so forth and so on. Many people try to argue that without social media, these protests wouldn't happen. I'm not so keen about it, but at least I can definitely see the value of social media in sort of coordinating the efforts of the individuals, but also allow to frame the entire conversation. What are the goals of the protests? What are the sort of reasons of the dissent? And so forth and so on. So in this sort of framework, and we analyzed a lot of these examples in our research at the Center for Complex Systems in the last 3 or 4 years. In this framework, under this framework, there are 2 important facts that we need to sort of acknowledge. We want to assess the credibility of the individuals behind the information spreading, and we want to also determine the veridicity and the accuracy of the information that spreads. And this is pretty much what we have been doing in in the context of the 2 projects that I'm going to present today. The first one is so-called social bot detection. A social bot is a sort of entity online that tries to mimic the behavior of a human, but it's essentially synthetic. It's an algorithm. It's a computer program that performs some actions like posting content on Twitter or following other individuals, interacting, generating, spreading information, news, and so forth and so on. Of course, it's really important to determine whether an account is a social bot. I will try to argue that in a second, the importance of the problem. But so essentially the task is this one, right? We have an individual. It can be a credible individual like the president or not. It's online, it's a persona, he has a profile. I want to determine whether this profile in Twitter is sort of governed by an entity, a human entity, or a computer program. So why do we care? Well, I want to argue, first of all, that the majority of social bots are designed to be harmful. So they are dangerous in a sense for our society. For example, these computer programs are used to run political smearing campaigns, deception campaigns, misinformation campaigns, and so forth and so on. We have very broad evidence of this. It's entirely bipartisan. For example, in the case of politics, it's not a left-leaning or a right-leaning strategy. Everyone does it. And of course, when these strategies are sort of unveiled, they sort of affect the credibility of the individuals, right? So there is something fishy already at this level, but I can argue that it's even more important than that. There is a huge implication in terms of economics, in terms of finance. For example, here at Indiana University, we have Johan Bollen, who is one of the early proposers of using social media data for training and predicting stock market fluctuations, right? What happens if social bots affect somehow the social media data stream and the conversation and create, for example, buzz or hype around the concept, around, for example, a name, a brand, an entity, a company, and this entity makes a profit out of it. This is what actually happened a few months ago. There is a guy, single guy in a garage, he started this company called Sync, And the company doesn't do anything. It's on the stock market. It doesn't produce any product or stuff like that. The only thing that this guy does in his garage is creating a legion of social bots online. At some point, he activates the bots. The bots start tweeting about sync. These high-frequency automatic trading algorithm pick this discussion, and they think that there is a huge buzz from thousands and thousands of people online about sync. So probably they're going to release some big product, some revolutionary technology, and they start trading like crazy the stocks. So in a few minutes, the company literally goes from a few $100,000 value to $5 billion. The guy cashes out and disappears, makes a lot of profit. So this is another effect, and many people, of course, are upset because they lost $5 billion in these fake stocks. There are many other examples of this, but I think I brought enough argument. They are used for spam, for social pollution, and so forth and so on. Sometimes bots are also created with different goals. For example, they might be benign, not necessarily harmful by design, but they can also be dangerous. For example, there are bots that retweet, rebroadcast information automatically. And per se, this is not a problem, but it becomes a problem when you spread misinformation, when you spread inaccurate facts, rumors. And this is what happened a few months ago when the Syrian electronic hacker army hacked into the Associated Press account, Twitter account, and wrote this tweet here, breaking news, 2 explosions at the White House, the president is injured. Of course, this never happened in the real world, but in the online world, what happened is that hundreds of thousands of retweets of this tweet spread online in a few minutes, and this has an effect in the real world. In fact, there was one of the largest 1-point drop in the stock market, actually in the Dow Jones, which caused $136 billion to vanish in a matter of minutes. And it took only 3, 4, 5 minutes to the Associated Press to realize that the account was hacked. They deleted the tweet, but the damage was already, done. So the problem of detecting bots online and in general synthetic conversation, synthetic activity is somehow of great social economic value. I'm going to show you an example of how our system works, and then I will give you like a 2 minutes overview of the technical aspects. There is this website, trudy.indiana.edu/bot or not. Everyone can access it as long as you have a Twitter account. You log in, and you can query any Twitter account. You just write the username of that Twitter account, and our framework essentially queries in real time the Twitter API and gets back the public information about this account, about the friends of this account, the contacts, the content produced by this account, and so forth and so on. And a lot of real-time analysis is run, and after a few seconds you wait, the machinery crunches the number and then gives you a likelihood score that this account is a bot, a social bot, or a human. If the score is low, like in this case, 12%, essentially our framework tells that the probability that the account you are analyzing is a bot is very low. And it doesn't only make this prediction based on the information of the user, but it does it using a wide range of information. For example, information about friends of these users, information about the content that this user posts, information about the sentiment of the content posted by the user, information about the temporal pattern of activity, such as tweeting, retweeting, and so forth and so on, network information or diffusion of his content, and much else. It doesn't give you only the likelihood. It also provides many interactive visualizations that allow you to make get some insights about this activity. For example, there is a sort of temporal patterns of consumption and production of tweets and retweets. On the right side here, we have the network of hashtag co-occurring in the content produced by this user, which means essentially the topics this person is interested in and posts about. And then we have other statistics and visualizations about the emotions, the sentiment of the content that this individual or bot produced, how the syntax of the language is used, and so forth and so on. So the gist is that maybe you cannot learn too much other than the prediction score if you look at one single account, but what you can do, you can run comparisons, right? So on the left-hand side of this slide, you have the analysis of my account. It says, well, I'm pretty much confident that you are not a bot, even though, it's still 26%. You might be a little bit a bot, right? But if I look at all the features sort of separate, all the features look like human behavior, right? On the other hand, on the right side, you have this Justin Bieber photo account. This is a bot. This is known to be a bot because there is a paper by Sune Lehmann, who is a professor at Denmark Technical University, who works on social bot design, engineering. So it creates essentially computer algorithms that mimic human behavior. Our system, in fact, is able to to determine that this account is governed by a bot. In particular, the determination is sort of strongly biased by not much the temporal pattern of production or the diffusion network information, but more really about the content and sentiment of the content. This makes a lot of sense because even though when we design bots, because of course from our side what we do is sort of try to reverse engineer the strategies of bot design. When we design the bots, we can do some things very well, like reproducing very credible temporal patterns of content production, imitating, the sort of circadian activity, the bursty behavior of humans. But some other things we cannot do that well. For example, content is really difficult to be produced because today, even though all the advances in natural language generation, still language models for generating human-like language are not good. Okay, so you can run all these comparisons, but at some point, we started learning something about our system, and I'm gonna make this parallel with Terminator 2. If you watch the movie, you know that there is, the character played by Arnold Schwarzenegger, which is essentially the old, unsophisticated robot. It's a very sort of basic cyborg, right? Under the skin, if you look very carefully, you can see the metal, and so forth and so on. This is the kind of bots that we can detect right now. We can detect the bots that look like human, but if you really look with maybe a little bit of attention or a magnifying glass at their features, you can find something fishy, like the metal under the skin, right? On the other side, on the right-hand side of the picture, there is the T-1000. The T-1000 is the most sophisticated robot in the movie, and in fact, he is so sophisticated that he can sort of evolve and change its shape to sort of cross the defenses system in the movie itself. And to make, to draw this parallel, our system right now is unable to detect the more sophisticated bots that evolve and change their behavior because they are, they exhibit features that are much more human-like. I'm gonna give you a 2-minute technical description of our framework before moving to the next section. We leverage several dimensions, several sort of classes of characteristics that you can identify in social media content. For example, as I said, the user metadata feature, the friends metadata, the timing, the content and sentiment, and so forth and so on. Then our system is constructed based on several classifiers. We don't invent any new classifier, any new machine learning framework. If you want, we take off-the-shelf machines, we train them with a data set that contains examples of 15,000 humans, 15,000 bots, so that the system can create a profile for human-like behavior, a profile for bot-like behavior, and then make a determination. And when we use this data set to evaluate the performance of our system, we actually do really well. We find out, for example, that on this dataset, specific dataset, 2 models, 2 classifiers perform fairly well, around 95% accuracy, which means essentially every time I see a bot, every time I make a prediction and I say this is a bot, then in 95% of the cases I would be correct, which is fairly good. Then we investigate a little bit more into the features that we construct to understand what are the characteristics that make bots more detectable, what are the features that are the best predictors. And without much surprise, we find out first that the best predictor is the user metadata. Twitter provides publicly a lot of metadata about the users. For example, your geographical location, if it's given, how many followers you have, and so forth and so on. These are the best predictors, the best features to make a prediction. And the second best features are the content produced. Because as I said, content sometimes can look a little bit fishy. We look into each of these feature classes independently. For example, take the user metadata, and we start learning really something about the bots and the humans, of course, on the other end. So what we find out, for example, is that bots produce way less new tweets than humans, but they produce way more retweets than humans. And this is kind of intuitive, once again. Producing new tweets, producing new content is difficult, but simply rebroadcasting, retweeting what other people say, it's costless, right? On the other hand, they have, for example, very long usernames, because sometimes the usernames are generated automatically by concatenating random strings, random characters. They are mentioned and replied way less than humans, because probably they produce not very interesting content, and therefore they are not addressed so often. We do this exercise with beneficiaries, and we learn, we learned a little bit about how sort of humans behave and perform on social media, and on the other hand, how social bots behave and how we can leverage this information to detect them. So this is sort of short summary of this part. And I try to convince you that this is, of course, a very interesting problem in terms not only of social, but also economical relevance. This was a very gratifying project. In fact, we got a lot of positive sort of feedback from many outlets like BBC, MIT Technology Review, and so forth and so on. But once again, in this hyper-democratic environment of the internet, we got also some critique. This is one great example. This Daily Dot article says, oh, the US government is spending about $1 million to figure out memes. And I mean, if you read the article, this makes sense. But unfortunately, well, there are some arguments that make sense, and they say, well, maybe this is not a really interesting problem. I argued differently, but everyone is entitled to his opinion. Unfortunately, the step is short from here to ending up, on Fox News, right? So there is Megyn Kelly, there is a full 4-minute service with some expert talking about how Indiana University and our team is building a sort of database of hate speech and stuff like that. In fact, the day after, even worse, Phil Menzer is on Fox News, and I assume no one is happy to be on Fox News, or for what that matters on any national broadcast if it's if you get some sort of a false statement or smearing attack in your of your work, right? So interesting fact: a few days after, of course, this story was debunked because it was sort of full of imprecise things. From the Columbia Journalism Review and from many other important news magazines. But the gist, I think you got it, is that at this point what we want to do is not only anymore assessing the value of a given account, but we want to move a step forward. We want to assess the value of a given entire conversation. Of course, this is a much more complicated task, right? We want to determine, for example, whether some entire conversation is a genuine, grassroots, organic, like in the bottom left part, or if you separate along, say, the information diffusion axis on the x-axis, you can have a conversation that is sort of sponsored, support, for example, advertised. And of course, here I'm not saying that advertisement is bad. Advertisement is just a mechanism of spreading information, and if you go to business school, they teach you how to do advertisement effectively. Simply, what I'm arguing is that our systems and ourselves, we need to be able to determine whether something is sponsored or not. It shouldn't be hidden, right? And on the same sort of line, if you look at the y-axis on the sort of credibility of information content, you can see that sometimes information is truthful, some other times information can be sort of misleading or non-accurate, and so forth and so on. If you combine these two dimensions, you get what we call complex persuasion, and eventually we want to go in the direction of being able to detect these kind of persuasion campaigns or campaigns online. So this is one example of our project. What we want to do is identifying and sort of predicting whether a trending conversation, and we focus only on trending conversations, which are those that attract a lot of attention, whether a trending conversation is organic, so people talk about it sort of grassroots, or is promoted. Someone is paying for it. Luckily enough, Twitter tells whether an hashtag, a given conversation is promoted or not, or is organic. So what we did was harvesting all these hashtags promoted and non-promoted during a long period of a few months. We got a fairly large data set. And then we have examples of organic versus examples of promoted hashtags, trending hashtags. And what I want to show very briefly is that this problem of separating hashtags which are promoted or not is very complicated even for humans. If you look at the right-hand side of this table of examples, you have some organic hashtags like Football Club Barcelona, Symbiotic Titans, The Undertaker, Only Westeros, All these hashtags are organic. They become trending organically from conversation on Twitter, but they all convey some brands, some entities, TV shows, sport teams, and so forth and so on, right? So if you know a little bit of marketing, good. This is good advertising, but instead it's spontaneous sort of organic conversation. On the other side, on the left side, you have some hashtags which are promoted. People are paying millions of dollars to make these hashtag trendings. Get happy, survive the night, make boring brilliant, it's not so complicated, and so forth and so on. These hashtags don't convey any brand, don't convey any entity, any product, right? So they are not the best examples of, sort of advertisement done right, but still these are sort of, examples of hashtags which have been promoted on Twitter. So even for humans, separating these in the right, categories would be very challenging. Imagine for a machine that doesn't know anything about marketing and stuff like that, right? So our goal is create a framework a computational framework that can do this in a smart way. Once again, we leverage all the features that I said before, but one important peculiar characteristic of our framework now is that it's not anymore a static snapshot like in the case of bots. I take a picture of the bot at this very moment, and I tell you, it's a bot or it's a human. In this case, we have the entire history of the conversation, and it's something that evolves over time. It's a temporal evolution. So we somehow leverage machine learning frameworks to encode these temporal patterns. And what we get is a machinery that eventually with something close to 87, 88% of accuracy is able to determine whether a trending conversation has been promoted or not. So we have a framework that this time dynamically over time is able to make predictions. In case you are curious, now there are not anymore some static classes of features that are best predictors all the times. Now the features predict, depending on when you make the prediction in time, closer to the trending point or after the moment this conversation became trending and so forth and so on, depending if you want to make an early prediction or a late classification, the features have different importance. For example, if you want to make an early prediction, the temporal patterns and the timing activity are very powerful, but if you want to make a later classification, the network and the sentiment of the content are extremely important. And this is, just to conclude, how our machine comes to a sort of outcome. On the right-hand side, you have Galaxy family. This was an example of promoted hashtag, and our machine correctly identifies that. On the other side, Galaxy S4 is an organic hashtag, correctly identified by our system. So to summarize also this and go towards conclusion, our system is able to allow us to make some fairly accurate prediction and classification of promoted versus organic conversation online. And this is done essentially leveraging the temporal evolution of these conversations in social media. Eventually, the stuff that I presented today goes under a larger umbrella of projects that we have here at SeaNets. And I hope you are interested in talking about these. We have been looking at trends, as I said before. We have been looking at social media protests like Occupy Wall Street, the Gezi Park protest in Turkey, and all of these got great feedback, and we are really proud of it. And this is another research line that I've been pursuing in parallel with a collaboration with the Army in Italy, which is about criminal network analysis, essentially using large-scale network data from mobile phone conversation, financial transactions, social media, so online social networks, interactions, and so forth and so on, to sort of detect criminal activity and sort of frame criminal suspects and find new criminal connections in the real world. And essentially, before concluding, well, this was also very successful. It ended up in the cover news of the communication of the ACM. So before concluding, I want to thank all my collaborators, the PIs of the project, Phil and Sandro, and all the students who worked on these projects. Without them, nothing of this would happen. Thank you. This is a pretty interesting question because, first of all, of course, I don't have a definitive answer. As an organization, there are many people who interact with the same account, plus some operations might be automatized, right? So, people might post content to the account, and then the account simply sort of dispatches the content over time, something like that. So in literature, there is a term for these bots. They are not social bots in the strict term, but they are called cyborgs. So they are a mixture of human and machine. And it's even more complicated to detect those because they exhibit way more human features than, generally speaking, for example, the content is generated by the humans. Yeah.
Machine learning study, there's 15,000 bots.
Yeah.
How do you identify the bots?
This is done, so this is done not from our group, but from James Caverly, Texas A&M. What they did was designing they call it social honeypot. Essentially, it's a trap. They create some accounts that generate gibberish, random, posts, meaningless. And then all the accounts that repost, retweets, or follow those accounts essentially are red flagged. They might be bots because they are not performing any activity that a human would do. They manually inspect those versus another ground truth sample of 15,000 humans, and then they manually validate each and all of them, and they come up with this data set that they shared for our training.
And is there an estimate on the number of?
So there is an official estimate from Twitter from December 2014, so 2 months ago, a month ago. Yeah, they say it's between 5 and 8%, but they talk about the content, not the users. So they say about 5 and 8% of content produced is synthetic, and their definition is very vague. So it's really unclear, how they compute that or what they include in this synthetic artificial content.
It's worth that point. It's worth mentioning that it's of Twitter's interest to be as vague as possible about the amount of fake content they're trying. Their public company is trying to make the point that all their stuff is fake.
Thanks again.